Well, welcome to lecture 13. It's been a day since I did lecture 12. And this lecture will be on clutter rejection. And it's the second half of the very large piece of material that I've divided into two lectures. And we'll look at Doppler filtering. And the other caveat will be that the radars that we're going to talk about today are all ground-based. But the general principles will apply in the following lecture, which will deal with airborne radar. And we're still one day away from Hurricane Irene. Looks like we might get a break, and I might have power tomorrow night. So let's move on with things. Here we have the block diagram of the radar system, which we've been going through piece at a time. And now we're going to look at clutter rejection using Doppler filtering. And the filtering that we were using before was a high-pass filtering system known as MTI filtering. And Doppler filtering is going to be with a set of passband filters. And we'll be going over that in detail now. First, there'll be an introduction. Then we're going to look at the problem perspective. Burst waveforms and their properties. That is to say, when we just don't send out one or two pulses and listen to the echoes for them, but we might send out 100 or even 1,000 pulses in a burst and waiting for the echo after each one of the, or echoes after each one of the thousands, and take those samples at given ranges and process those samples through a linear process, multiplying them by weights to get the output of a specifically shaped filter, which will have specific frequency properties in the Doppler domain to optimize our detection. And this whole process of Doppler processing was enabled by the important technology advances I mentioned in the previous lecture, and then we're going to look again on the impact of Moore's law, past, present, and future. And then we'll move on to a series of half a dozen topics, and they will be pulse Doppler processing techniques. We'll go into detail about pulse Doppler processing, and then we're going to look at a low PRF example, the moving target detector processor that was first employed in the ASR9, and how now, let's see, it was developed in about 75, and it reached the ASR9 about 15 years later, and now we've gone even past that in technology. So I'm going to show you really the old technology, but as I show it to you, I'm going to point out that that can be done in a PowerPC board right now. Just to let you know, I think an important thing to understand in radar signal processing and data processing from sensor systems is with that, we're not on an even base. Technology isn't even. It's in processing. It's continually to make great advances. Then we're going to look in detail at the range Doppler ambiguity problem. And then we're going to look at resolving the ambiguity problem and one specific method, the Chinese remainder theorem. And then we're going to look at the ambiguity function, which is a three-dimensional visualization of range Doppler space of the waveforms that we use. And then we'll do a quick review of airborne pulse Doppler issues before we summarize this lecture to the next lecture, which will be on airborne pulse Doppler issues. Okay, now let's just go back. We looked at MTI radars in specific, and we found out that you could indeed suppress ground clutter pretty well if you had A to D converters with wide dynamic range and very high sample rates, but they were high-pass filters, and they'd have a difficulty with clutter that had a spread to it. And rain clutter is that nemesis where MTI and C clutter also to a significant extent are places where they're a real nemesis for pure MTI systems. And then we also have birds, which are real targets. And we're going to talk about those in relation to pulse Doppler processing. A one filter with a notch at 0 will not adequately reject rain. And that's just a plain fact. Right now we've got rain coming up the coast that has a mean Doppler velocity of 25 to 30 knots. That's the velocity of the hurricane. But lots of times fronts will move in that aren't the size of a hurricane, which is 300 miles in diameter. But there'll be rain, there'll be patches of rain and lines of rain clouds that will come in, and they'll move at 20 to 30 knots, a very healthy mean velocity, and there'll be a spread of that velocity also. And this is just one Doppler spectrum to give you living proof that indeed rain has a Doppler spread to it, and it has a non-zero mean. It's just MTIs won't handle it. Move on. Now the issues with the MTI cancellers. Typically they process, as you remember, 2 to 5 pulses at a time, so it's nearly impossible to shape them as you would if the filter had an input of 10 pulses or greater. You can make a filter that looks a set of filters which look very, very square when you're using if you had 1,000 pulses to do the processing. But when you're dealing with 2 to 5 pulses, you just have 2 to 5 degrees of freedom in your weights. And with that, you can't get the low Doppler side lobes you need to suppress the rain that's in the side lobes, filling up that unambiguous Doppler space. So a 2-pulse cancel is a very broad in Doppler space. 3-pulse cancel is quite similar. And 5 gives you very high side lobes. As little as 15 to 20 dB, which isn't enough to reject the rain. A set of Doppler passband filters with a minimum of 8 to 10 pulses can be constructed to set a notch at 0 Doppler that can reject the ground clutter, and a set of passband filters that can detect targets where no rain is present. And before the mid-70s, the technology to cost-effectively implement this kind of a pulse Doppler solution was not available. To kill my own thunder, I can buy with 5-power PC boards off the shelf and program them to do this job. But in '75, it took 1,000 integrated circuits to do it. But cost-effectively for that time of day, you could implement that on a radar. It was a small fraction of the cost of the radar to solve a big radar problem for the air traffic control people. But now it's peanuts. Effectively, the cost of the processor is such a small fraction of the cost of the entire radar. You shouldn't think about it, and you should process as many pulses as possible to get the Doppler filters down nice and low and have good characteristics to the Doppler passbands. Okay, first let's look at burst waveforms and their properties. By that I mean sets of pulses at a given PRF that will be n long. And that burst we call a coherent processing interval. Remember this from when we were talking about MTI filters. Burst waveform offers a method of collecting M sequential samples from each range cell. And remember, we were talking at pulse 1, at the 13th sample, it was at 4.6 kilometers. The second pulse, we could collect the same sample, at which would be at the same range, same echo time, pulse 3, up to m pulses. So we can do this and get lots of pulses. And a burst waveform offers a method of collecting m sequential samples for each range CPI cell. And these samples can be linearly processed through a set of passband filters that will detect targets within a range of Doppler velocities and simultaneously reject the clutter that is in their low side lobes. You want really low side lobes so that the distributed clutter, such as rain or chaff, won't leak into your passband that your target is in. And if the passband filters are narrow enough in frequency, a measurement of the Doppler velocity of the target that passes through them successfully can be made. So you can also, with these waveforms, measure the Doppler velocity of the target and see if it's consistent with the rate of change of the range in progressive scans of the radar as it goes around, which is another example. And now let's look at the impact of Moore's law, past, present, and future again. Now, this is just to grind into you the history. In the 70s, a 5-bit, in the 1970s, a 10-bit 5 megahertz A to D converter was near the commercial state of the art. It was 30 pounds and 3 inches of rack space. Now, it's not only on a chip, but many more bits and much higher sample rates are available. That's Moore's law. For a 60 nautical miles airport surveillance radar with a mechanical scanning antenna, as we've been talking about, it allows us to individually calculate the millions of range Doppler azimuth cells response, from several thousand to several million per radar scan. And these advances allow aircraft to be reliably detected in rain with much better detection of radar and ground clutter and very low false alarm rates that allow the radar and beacon sensor on the air traffic control radar system to be seamlessly integrated. In the future, expected advances in processing techniques will allow new techniques. I'm talking about algorithmic techniques. Now, what we're going to do is we're going to propose a specific set of weights for the entire radar. But some of the new techniques which you can do is measure, if you're familiar with these terms, measure the Doppler, I'll say it in a lower level language, measure the power spectrum of the clutter in each range azimuth cell, and then calculate what would be the optimum weights for that individual cell. Now, to do that, you have to take a set of measurements, average them, and develop a covariance matrix. And you're going to have to invert those covariance matrices for hundreds of thousands of times per scan. That's the kind of thing that potentially the great advances will allow one to do. And with a ground-based radar, just looking at the time Doppler domain. I've not yet talked about other things. We'll get to those in one of the lectures, which I haven't developed the view graphs for yet, but which will be coming. And now on to pulse Doppler processing techniques. I want to talk about them to start off and to end this first section. Just to remind you, this is our set of pulses, and this is the pulse repetition interval. This is the pulse width, and this is the unambiguous range of the radar. If we change the time axis to a range axis, they're linearly related. And so these, remember that the returns from here would alias down to here, and the negative ones would alias up. And that we're talking about processing data from n pulses, and we call that a coherent processing interval, those n sets of pulses. And we're going to process that data for each range azimuth cell. And for an FAA radar, we're going to process 10 pulses coherently, then change the PRF to 10 more pulses we'll process independently at a different PRF to resolve ambiguities for this particular radar configuration, an airport surveillance radar. Okay, now here we go back to our diagram. I'll just assume you remember these things. We take the data. Remember, this would be the complex samples. Should be a 2-hour, well, that goes through the A to D converter, the real and imaginary parts of the data. It's those samples which together make up the complex envelope of the receive. And you remember that the pulse number goes this way in the matrix, and the sample number, that is range, goes this way, where this dimension is m, the number of pulses in your coherent processing interval, and this is the range, the number of range samples. In the airport surveillance radar, there are about 1,000 range cells, 1/16 of a mile each over 60 miles. And they're going to have a set of 10 and then another set of 10 pulses. And what we want to do is we want to say, what's the optimal way to process the M voltage samples in a range gate to detect the target and reject the clutter? And this is how we do it in a generic sense. We've got this set of M samples, complex samples coming in, and we send them through M different filters. And these filters are characterized by a set of weights. And there'll be an output from each filter. And notice each filter is going to cover a certain passband that overlaps slightly, but clearly a target which had this Doppler velocity would not be seen in this. These are log scales, and this would represent, say, 0 dB, and this would be 40 dB or so, 30 or 40 dB. So you can see these are log in the side lobes. This is in Doppler velocity, Doppler frequency. We're coherently integrating all the pulses in a CPI. Now, this number of filters could be very large. It could be 1024 in airborne radar sometimes, or 512, 1632. And then we can do clutter rejection and resolving the targets into different velocity segments and allowing for fine-grained target radio velocity estimation. This is generally what we would like to do. And we're going to come out with a number of Doppler velocity bins for each range CPI. There are 2 CPIs per azimuth beam width cell. And so coming out, every scan of that airport surveillance radar is forgot the number. It's in the order of magnitude of 3 million range azimuth Doppler cells that come out of it. So, and we're going to have to threshold those in a manner so that we see the targets, don't see the noise. Back to our detection lectures. Okay, now I just want to remind you from before, the MTI improvement factor that we previously introduced. That's the ratio of the signal to clutter out to the signal to clutter in. The next question is, in the presence of colored noise, ground clutter, rain, and noise, what are the weights we should use to multiply the M input signals, S sub I, in order to maximize. And note that the optimum set of weights depends on the frequency. I think I showed you in the definition I had down here in F sub D. I think I'll change it on the PDFs. That's 14. Okay. Now, in the late 1960s, the theoretical solution to this was developed by two independent researchers, and you can look at them and their formal content. One was published in the IEEE Transactions on Aerospace and Electronic Systems, and independently one was published almost in the same month in the Information Theory Transactions. They were developed independently by two different groups of people, Rumler at General Electric, and Ed Hofstetter and Darrell DeLong at Lincoln Laboratory. And I think they were in touch, so they acknowledge each other in their papers. And it's interesting that they used sort of a different formalism, slightly different. So you look at one paper in a superficial manner, and you say, okay, 5 seconds. And you look at the other one, it doesn't look like they're saying the same thing. They're saying exactly the same thing. And this is what it is. The whole paper boiled down. Only what they do is they prove the answer. The problem is, what is the optimum way to maximize the signal to total noise, clutter, and interference to linearly process M-complex radar returns, the V sub i's, in the presence of these backgrounds? And the answer is this. The result is, in power, it's the sum of a set of weights times the voltages. And what is the optimum MTI improvement factor? The optimum MTI improvement factor as a function of frequency is the sum of the signal vector, each element, summed over, excuse me, this I should be a K, because we're going to sum over K. Add one more to be fixed. It's nice how giving the talk is an excellent way to debug your view graphs. So, and it's multiplied by a set of optimum weights, which here I define. And they prove that this is the optimum set of weights. The optimum set of weights are an arbitrary constant times the sum of the inverse of the covariance matrix of the clutter, noise, etc., times the signal vector in this manner. And where V sub i's are the sampled voltages, S sub I is the signal vector, M sub I again is the covariance matrix of the noise, etc., and M is the number of pulses processed. Okay? Here are these optimum weights. Now, how do we get them? And I'm going to tell you right now, the easiest way to think about the covariance matrix in simple terms, for me, the simpleton, is to say, look at what the clutter spectrum is. The first thing you do is you take the power spectrum, sample it, and take its Fourier transform. That Fourier transform is the autocorrelation function of that clutter with its spread. And you sample that autocorrelation function at your sample between pulses. And that is this covariance matrix that you have to take the inverse of. Now, if you have 100 pulses, that means you have to integrate, take the inverse of 100 by 100 matrix. It's technically stressing. And so you can see that it's a much more straightforward factor to in 1975 it was, to take the path that was taken to develop the MTD with the hardware available. But I want you to know that right nowadays, what people would do is they would use this formalism to develop the optimum weights. In Lecture 18, these issues will be studied in a lot more detail, and see also reference 9. Herman Rowling put together a great, instructive, readable reference on this material, and in 2 volumes of a European journal. You may be able to get a hold of it if your library, your technical library at your university has excellent resources. Herman's an old buddy, and he sent me a copy of the original reprint, and I had, one time I had 100 copies made, passed out to individuals and friends, and another time at Lincoln Laboratory we got the original and we made 50 copies or so. I know one is in the Lincoln Laboratory library in PDF form, and there are others available. Maybe Herman can get you a reference on the web. In reference 9, you can find out more about that. Because of the variable nature of ground and rain clutter, a simple high-pass filter, an MSI Canceller, using 2 to 5 pulses will not come close to simultaneously rejecting both the ground and the rain. We've been drilling that into you. You need at least 8 to 10 pulses are required for good rain rejection. Much rain clutter will pass through that high-pass filter. And typically, a set of, or a bank of Doppler filters is used in parallel over the range of Doppler velocities from 0 to the blind speed, and the number of filters used is typically the number of pulses processed. Now, if you use that optimum processor calculation to say, I have 10 pulses that are returned from a dish this size that's rotating this fast of an airport surveillance radar, and at this PRF, and I have about 21 pulses of beam width, and I have my natural, the natural clutter, which is very small, but I've got the amplitude modulation, which is explained in Skolnick and is explained in Barton's books. That will amplitude modulate those pulses and will spread the clutter, so that for each and every Doppler filter, in theory, I calculate what would be the optimum processing filter. And I overlap all, in this case it was 1,001 filters. This is the envelope of a 10-pulse optimum processor. But when you process 10 pulses, you're going to get an overlap that's pretty good, and if you don't get it in one, you'll get it in the other. It fills in the notches pretty well. And you see there's a lot of space in here that a 10-pulse optimum processor will see and improve the Doppler detection performance, the MTI improvement factor, than a 3-pulse canceller, which is very close to the optimum processor for 3 pulses. So you can get a lot better performance in rejecting ground clutter, but we still have to deal with rain, and we'll be seeing how we do that in a moment. And what we're talking about, as I said before, is 1,001, so this is blue as a continuous line. Here is an optimum filter tuned to 300 hertz. Well, I haven't told that optimum filter anything about my rain yet. I've just said, you've got ground clutter. What's the optimum filter look like? So it gives me 13 dB side lobes, as you'd expect. So this will reflect, will optimally reject ground clutter and noise. That's just one of a set of 10 filters you could put that will do that job. Now, here is one way we can set up a simplest way to implement a bank of filters with a discrete Fourier transform is we can just run 8 filters through a discrete Fourier transform and we'll get 13 dB side lobes. This is a magnitude on a linear scale, and this goes from 1 to 8, right over here. I should have added in the numbers, I'll do that. Just a linear scale, in relative speaking of the. And here is the Doppler filter bank of 8 filters that are shaped to have low Doppler side lobes. And you notice they're down the order of 35 dB in most cases. So weighting of the FFT is a simple way to along with adequate number of pulses of giving excellent target detection, even in the presence of rain. Now I'm going to take a stop here and put in a break, and then we're going to look at the low PRF example of how the MTD was implemented and show you some of the performance that it gave, and which obviously you could get with a different hardware implementation.